You start with nothing, then you move, and you keep on moving till you can't get any more, then you're done. StatQuest, bam. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about optimization with linear programming, main ideas. Specifically, we're going to talk about the main ideas behind the Simplex algorithm. This StatQuest is brought to you by the letters A, B, and C. A always, B, B, C curious. Always be curious. This StatQuest is also brought to you by Gurobi. Gurobi, which has always been free for academics, provides a state-of-the-art optimization solver used by leading companies around the world. Gurobi powers decisions in logistics, energy, finance, and beyond. If your goal is not just to understand optimization, but to put it to work, Gurobi is the solver trusted by experts. To learn more, check out the links in the description below. If you've ever wondered about how flight schedules are optimized, warehouse inventory was optimized, or crop selection was optimized, then, without knowing it, you've wondered about linear programming. Linear programming is a field that comes up with clever algorithms for optimization. And that's what we'll learn about in this quest. Now, imagine we owned a factory that made cookie and donut mixes. And each kilogram of cookie mix resulted in $3 of revenue, and each kilogram of donut mix resulted in $2 of revenue. In other words, we can calculate the revenue with this equation. 3 times cookie mix plus 2 times donut mix equals revenue. And our goal is to maximize the revenue. Josh, maximizing revenue is easy. Just make huge amounts of cookie and donut mix and sell them all. Not so fast, Squatch. Although we want to maximize revenue, we only have 10 kilograms of flour. And each kilogram of cookie mix needs 0.4 kilograms of flour, and each kilogram of donut mix needs 0.5 kilograms of flour. In other words, the amount of flour that we use to make cookie mix, plus the amount of flour we use to make donut mix, needs to be less than or equal to 10 kilograms. That means that even though we want to maximize the revenue, we can't just make as much cookie and donut mix as we would like, because we can only use, at most, 10 kilograms of flour. Now, if we don't make any donut mix at all and replace it with a 0 in the equation for flour, then we can solve for cookie mix and see that we can make, at most, 25 kilograms of cookie mix. And thus, given this graph that has cookie mix on the y-axis, and donut mix on the x-axis, we can put a dot at 0,25 to represent 25 kilograms of cookie mix and 0 kilograms of donut mix. Likewise, if we don't make any cookie mix at all and replace it with a 0 in the equation for flour, then we can solve for donut mix and see that we can make, at most, 20 kilograms of donut mix. And we can put a dot at 20,0 to represent 20 kilograms of donut mix and 0 kilograms of cookie mix. Now we can join those two dots with a line. And anything from that line and below, in this yellow area, will satisfy the constraint on how much flour we can use. However, since it doesn't make any sense to make negative amounts of cookie and donut mixes, we can restrict our attention to the area that only allows for amounts that are greater than or equal to 0. In other words, we can pick any point in this yellow area and know that it represents a feasible combination of cookie and donut mixes that use less than or equal to 10 kilograms of flour. Oh no, it's the dreaded terminology alert. The corners of the yellow area are called vertices, and each one is called a vertex. Now we need to find the point in the yellow area that results in the largest revenue. And we can start by calculating the revenue for each vertex. In this case, the vertex at the origin, 0, 0, gives us the worst revenue. Because when we plug zeros into the equation for revenue and do the math, we get 0. In other words, if we don't make any of the mixes, we won't make any money. So we can remember this, we'll label the origin with its revenue value 0. Now we can calculate the revenue for the vertex where we make the maximum amount of cookie mix by plugging in 25 for cookie mix and 0 for donut mix. And we get 75. And we can calculate the revenue for the vertex where we make the maximum amount of donut mix by plugging in 20 for donut mix and 0 for cookie mix. And we get 40. Now that we know how much revenue we can create at the 3 vertices, let's figure out the revenue along the edges. First, we'll focus on the edge where we only make donut mix. The revenue along the donut mix axis goes from 0 at the origin to 40 at the vertex 20, 0. And if we don't make any cookie mix and replace it with 0 in our equation for revenue, then we see that the only way to maximize revenue is to maximize the amount of donut mix that we make. In other words, if we plug in a value for donut mix less than 20, then we'll get a revenue value less than 40, the value at the vertex. Now let's focus on the edge where we only make cookie mix. The revenue along the cookie mix axis goes from 0 at the origin to 75 at the vertex at 0, 25. Now, if we don't make any donut mix and replace it with a 0 in the equation for revenue, then, in this case, we see that the only way to maximize revenue is to maximize the amount of cookie mix we make. In other words, if we plug in a value for cookie mix less than 25, then we'll get a revenue value less than 75, the value at the vertex. To summarize what we've seen so far, if we only consider revenue along these 2 edges, then we see that the most revenue is created at the vertices, and the maximum revenue, so far, is at this vertex. Now let's look at the revenue along this edge. The revenue along this edge goes from 40 at the lower vertex to 75 at the higher vertex. And if we calculate the revenue for points in between the vertices, we see that it increases until we get to the maximum value, 75, at the vertex at 0, 25. And in general, whenever we have a straight line that represents a higher revenue on one end and a lower revenue on the other, any point on that line between its vertices will have some intermediate revenue and never the highest or the lowest. Lastly, let's talk about the revenue for an internal point like this one. Just by looking at this point, we can see that we could easily make more cookie mix, and thus make more revenue. Or we could make more donut mix, and make more revenue. Thus, internal points can never maximize revenue because we can always make more stuff. As a result, if we want to maximize revenue, we don't have to calculate it for every single feasible combination of cookie and donut mixes. Instead, we only have to identify the vertex with the largest value for revenue. And, in this example, making 25 kilograms of cookie mix and 0 kilograms of donut mix results in the maximum revenue, 75. Bam! Now, this example was pretty simple. We only had 2 different mixes to worry about, and we only had one constraint, the total amount of flour on how much of each mix we could make. As a result, we could easily draw the shape of feasible solutions and calculate the revenue for the shape's 3 vertices, and pick the vertex with the largest revenue. However, it's much more common to have more than just one constraint. For example, we might also have a maximum of 5 kilograms of sugar to work with. And if we draw a blue line to represent the constraint on the amount of sugar we can use, we end up with a new shape that defines the region of feasible solutions that has an additional vertex. Likewise, we might also have a constraint on the amount of chocolate we can use. And that adds another vertex to the shape that defines the feasible solutions. In other words, the more constraints we have, the more complicated a shape we can end up with. Now imagine we had 3 different mixes we could make: cookie, donut, and brownie. Having 3 variables in our equation for revenue means we'd have 3 axes on our diagram. And if we only had to worry about how much flour we used, we'd end up with a relatively simple 3-dimensional shape. In this case, we could still calculate the revenue for each vertex and pick the largest value. However, if we had more than 3 mixes, then we can no longer draw the shape and look at it. And if we had more than one constraint that had to be met, then the shape, which we can't see, could be a lot more complicated.
Josh, if we can't see the complicated shape, what are we going to do?
In theory, we could still brute force the math, like we did in the previous example, and solve for all of the vertices and calculate the revenue for every single vertex, even for a complicated shape in high dimensions. However, in practice, using the brute force method can take way too long. The good news is that there's a whole field called linear programming that comes up with clever algorithms to efficiently find the optimal solutions. One of those clever algorithms is called the Simplex Algorithm, so that's what we'll learn about now.
Bam!
Note, for the rest of this quest, we're going to focus on the main ideas of how the Simplex Algorithm works. However, if you're also interested in the mathematical details, check out the follow-up quest.
I'm so excited about the follow-up quest.
Anyway, to illustrate the main ideas behind how the Simplex Algorithm works, we'll start with just 2 mixes, cookie mix and donut mix. And we'll add a constraint on the total amount of flour we can use, and a constraint on the total amount of sugar we can use, and a constraint on the total amount of chocolate we can use. As a result of these 3 constraints, we have a shape with 5 vertices that contains the feasible solutions. And the goal of the Simplex Algorithm is to quickly find a vertex that maximizes the revenue. Hooray! It's the main idea alert! The goal of the Simplex Algorithm is to quickly find a vertex that maximizes the revenue. Now let's step through how the Simplex Algorithm uses these equations to find the vertex that maximizes the revenue. Note, there are several variations on the Simplex Algorithm, and, for this example, we'll focus on one of the most common. That said, all of the variations have the same goal, which is to efficiently find the optimal values that maximize revenue. Anyway, starting from the origin, the Simplex Algorithm has to decide if there is a neighboring vertex that will result in more revenue. In other words, the Simplex Algorithm has to decide if it should explore along the cookie mix axis, or if it should explore along the donut mix axis. To make this decision, a simple and common approach for the Simplex Algorithm is to just pick the direction that generates the most revenue per kilogram. In other words, we can just look at how much revenue a unit of each mix will generate, and pick the one with the larger value. In this example, each kilogram of cookie mix increases revenue by 3, and each kilogram of donut mix increases revenue by 2. So we'll select the cookie mix axis because a kilogram of cookie mix results in more revenue than a kilogram of donut mix. Note, if there is a tie for the maximum revenue, the Simplex Algorithm just goes with the first one listed. Anyway, then the Simplex Algorithm moves from the origin to the first vertex on the cookie mix axis, 0, 10. This vertex represents 10 kilograms of cookie mix and 0 kilograms of donut mix. And thus, the vertex represents a revenue of 30. In other words, moving to the vertex at 0, 10 results in an increase in revenue compared to where we started at the origin. Now, if we make 10 kilograms of cookie mix, then we will use up all of the chocolate that we have, because 0.1 times 10 is 1, and we only have 1 kilogram of chocolate. In other words, we can't go any higher along the cookie mix axis, and that means we can't make any more than 10 kilograms of cookie mix. However, donut mix doesn't use any chocolate, and we still have enough flour and sugar to make some donut mix. So the next thing the simplex algorithm does is decide if the current vertex, 0, 10, has the optimal coordinates that maximize revenue, or if it should move to the right and increase the amount of donut mix that we make. Moving to the right would get us to a new vertex at 10, 10. And the new vertex represents an increase in the revenue from 30 to 50. Because moving to the new vertex results in an increase in revenue, the simplex algorithm decides to move to the right along the donut mix axis to the new vertex. Now the simplex algorithm has to decide if the current vertex has the optimal coordinates that maximize revenue, or if it should move to the next vertex at 7.1, 14.3. Because the next vertex results in a lower revenue, 49, the simplex algorithm decides that it would be better to stay at the current vertex, 10, 10, because it results in a higher revenue, 50. And that means that the simplex algorithm has found the optimal vertex, 10, 10. In other words, the simplex algorithm moves from vertex to vertex until it no longer increases revenue. In this example, that means the simplex algorithm stops at the vertex 10, 10. Note, at the beginning of this example, we started by going up along the cookie mix axis, because we would make more revenue per kilogram of cookie mix than we would make per kilogram of donut mix. But this is just one way to decide which direction to go. Alternatively, we could have just as easily decided to go out along the donut mix axis. Because, compared to the origin, where we wouldn't make any money at all, moving out along the donut mix axis also increases the revenue. And if that is what we had decided to do, then the good news is that as long as we keep moving to vertices that increase revenue, we'll end up at the same vertex, 10, 10. In other words, as long as we move when we can increase revenue and stop when we can't, we'll end up at the same vertex, 10, 10. Either way we do it, given these constraints, we can maximize revenue by making 10 kilograms of cookie mix and 10 kilograms of donut mix.
Double bam!
In summary, the simplex algorithm finds amounts of cookie and donut mixes that maximize the revenue, given these constraints, by starting at the origin, and then increasing revenue by moving to neighboring vertices, until moving to the next vertex does not increase the revenue. Bam! Now that we've seen the main ideas behind the simplex algorithm with a simple example, let's see what it does with a fancier example. However, before I dive into this slightly fancier example, I need to give credit where credit is due. The next example is loosely based on one in Robert Sedgwick's 1983 book, Algorithms. And I discovered it on Daniel D. Souther's webpage for a course taught at the University of Hawaii at Manoa, and the link is in the description below. So, with that said, now the goal is to find the amounts of donut, cookie, and brownie mixes that will maximize revenue. And now we have 5 constraints. Blip, bloop, bloop. Because we now have 3 variables we need to optimize, donut, cookie, and brownie, we'll draw everything on a graph with 3 axes. The first constraint creates this plane, and each remaining constraint creates a different plane. Now, if we assume we can't make negative amounts of donut, cookie, and brownie mixes, we end up with this three-dimensional surface. And the optimal amounts of donut, cookie, and brownie mixes that maximize revenue are defined by at least one of these 12 vertices. The goal of the Simplex algorithm is to efficiently find a vertex on this shape that maximizes revenue. Just like before, the Simplex algorithm starts at the origin and then has to decide if it should move along the cookie mix axis, or along the donut mix axis, or along the brownie mix axis. Like we did in the last example, we'll try to select the direction that has the largest increase in revenue per unit. However, this time, all mixes have the same increase in revenue per unit. So we'll just pick the first one, donut. Alternatively, we could have calculated the revenue for each direction and selected the direction that increases revenue the most. In this case, either way we make the decision, we end up going to the same vertex, 8, 0, 0. Now, to calculate the revenue for the vertex at 8, 0, 0, we plug 8 for donut and zeros for cookie and brownie into the equation for revenue. And when we do the math, we get a revenue of 8 for this vertex. Next, the Simplex algorithm has to decide whether or not it found the vertex with the optimal coordinates, or if it should go up and over a little bit more to 12, 3, 0, or out along the brownie axis to 8, 0, 4. Again, there are multiple ways to make this decision, but all of them share the idea that if we move, we need to move to a vertex that results in more revenue. For this step, we'll decide where to move based on which option will result in the most revenue. So we calculate the revenue at 12, 3, 0 and get 15. And the revenue at 8, 0, 4 is 12. Now, of the three options, the vertex at 12, 3, 0 results in the largest revenue. So that is where we decide to go. Then we repeat the process of choosing to either stay at the current vertex or move to another based on whether or not moving will increase revenue, until moving to another vertex no longer increases the revenue. So, in this example, this vertex, 9, 9, 4, represents the optimal values for donut, cookie, and brownie mixes, because moving to any of the other neighboring vertices will result in less revenue. Thus, after 4 moves, the Simplex algorithm has found a vertex that gives us the values for donut, cookie, and brownie mixes that maximize revenue.
Triple bam!
Now it's time for some shameless self-promotion. If you want to review statistics, machine learning, and AI offline, check out the StatQuest PDF study guides and my best-selling books on machine learning, neural networks and AI, and statistics at statquest.org. There's something for everyone. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, consider contributing to my Patreon campaign, becoming a channel member, buying 1 or 2 of my original songs or a t-shirt or a hoodie, or just donate. The links are in the description below. Alright, until next time, Quest on!